Every time you flip a light switch, you're tapping into one of humanity's greatest engineering achievements, a massive electrical grid spanning millions of miles. But here's something most people never think about. The electricity traveling to your home might be moving at voltages as high as 765,000 volts. That's 3/4 of a million volts. Touch it, and you'd be vaporized instantly. Yet when that same electricity reaches your neighborhood transformer, it's been stepped down to just 240 volts, the relatively safe level that powers your appliances. Why go through all this trouble? Why not just generate electricity at 240 volts and send it directly to your house? The answer is both elegant and profound. High voltage transmission saves enormous amounts of energy. Not a little, not marginally. We're talking about the difference between a functional civilization and one that would waste more than half its generated power before it ever reached a single outlet. Today, we're diving deep into the physics, the economics, and the engineering brilliance behind high-voltage power transmission. This isn't just about wires and transformers. It's about why our modern world is even possible. The problem. Let's start with the fundamental challenge that keeps electrical engineers up at night: electrical resistance. Every material that conducts electricity, copper, aluminum, even superconductors at room temperature, opposes the flow of electrons to some degree. This opposition is called resistance, and it's measured in ohms. When electrons push through a resistant material, they collide with atoms in the conductor. These collisions don't stop the flow, but they do something problematic. They generate heat. Here's where we encounter our first crucial equation: Ohm's law. The voltage drop across a conductor equals the current multiplied by the resistance. V equals I times R. Simple enough. But power loss follows a different, more brutal formula. The power lost as heat in transmission wires equals the current squared multiplied by the resistance. P equals I squared R. Notice what's happening here. The current is squared. This means if you double the current, you don't double the losses, you quadruple them. Triple the current and losses increase ninefold. This exponential relationship is the enemy of efficient power transmission. Let's put real numbers to this. Imagine a power plant generating 100 megawatts of electricity, enough to power roughly 100,000 homes. If we transmit this at a typical household voltage of 240 volts, we need to calculate the current required. Power equals voltage times current. So current equals power divided by voltage. 100 million watts divided by 240 volts equals approximately 416,667 amps. That's not a typo. 416,000 amps. To put this in perspective, the main breaker in your house probably handles 200 amps. We're talking about 2,000 times that amount flowing through a single transmission line. Now, let's calculate the losses. A typical high-voltage transmission line might have a resistance of 0.02 ohms per mile. If our power plant is 100 miles from the city, total resistance is 2 ohms. Using our power loss formula, 416,667 amps squared multiplied by 2 ohms. The result is staggering. 347 billion watts of power loss. That's 347,000 megawatts lost as heat. Over 3,000 times more power than we're even trying to transmit. It's thermodynamic nonsense. The wires would melt instantly, and we'd lose infinitely more energy than we delivered. This extreme example illustrates why we can't transmit meaningful power at low voltages. The physics simply forbids it. The resistance in practical conductors, combined with the squared relationship in the power loss formula, makes low-voltage transmission over distance physically impossible at scale. The solution. So we face a dilemma. We need to move massive amounts of power. We can't change the resistance of our wires significantly. Copper and aluminum are already excellent conductors, and exotic alternatives like silver are economically impossible. The distance to our cities is fixed by geography. What variable can we control? The answer lies in rethinking our approach to the fundamental power equation. Recall that power equals voltage times current. P equals V times I. This relationship is inviolable. For any given amount of power we want to transmit, we have a choice. We can use high voltage with low current or low voltage with high current. The power delivered remains the same, but the consequences of our choice differ dramatically. Here's the insight that transformed electrical engineering. If we increase the voltage by a factor of 100, we decrease the current by the same factor of 100 to deliver the same power. But because power loss depends on current squared, reducing current by 100-fold reduces losses by 10,000-fold. Let's revisit our 100 megawatt example, but this time transmitting at 240,000 volts, 1,000 times our original voltage. Now our current is 100 million watts divided by 240,000 volts, which equals 417 amps. Manageable. Practical. Running this through our loss calculation, 417 amps squared multiplied by 2 ohms of resistance over 100 miles. The result? Approximately 347,000 watts lost. That's 0.347 megawatts lost out of 100 megawatts transmitted, a 99.65% efficiency. Compare this to our low-voltage nightmare. By increasing voltage 1,000-fold, we reduced losses from an impossible 347 billion watts to a manageable 347,000 watts. That's a million-fold improvement in efficiency. This is why high-voltage transmission isn't just better, it's the only viable approach for moving electricity across continents. Without it, the electrical grid as we know it couldn't exist. We'd be limited to power plants in every neighborhood, burning fuel locally, accepting the pollution and inefficiency because distant transmission would waste more energy than it delivered. The relationship between voltage and efficiency isn't linear. It's exponential in our favor. Every doubling of transmission voltage quarters the resistive losses for the same power delivered. This is why electrical grids worldwide have steadily increased their maximum transmission voltages over the past century, climbing from 110 kilovolts in the early 1900s to 765 kilovolts today, with experimental lines reaching 1,100 kilovolts in China and 1,200 kilovolts in India.